Okay, everyone, welcome back to HLSC 3410. I hope that you didn't miss me too much. I'm excited for lecture today to get back into the material. I hope you enjoyed last lecture. Is there anything glaring that you all wanted to discuss in relation to the material? And then we'll talk about the labs because I have had a lot of emails in relation to that. Pull up the chat screen. Any questions? Oh, here we go, Lekka. But in the lab, will the TA be going over lab chart reader? We should figure it out. No, they'll be going over it. So I don't know if you had all seen, but there's an announcement for each of the different TAs. I think some of the TAs emailed you individually as well with a Google Meets link and a time as to when they would be holding drop-in sessions for students to log in and then go over just the protocol of how to do the labs and sort of what is expected, and then how to download and use lab chart reader, how to upload the lab report, how to do the quizzes potentially. Any questions that you guys or that any of you would have in relation to the lab, that is what the drop-in sessions are for. They're not mandatory in terms of attendance, because remember, the labs are all on your own time. And the second thing that I've had a lot of emails about is that with the restrictions lessening, there will be some courses going back onto campus. For this course, though, just to put it in bold, it will be staying in the format that it is right now. So all virtual and all sort of on your own times with the quizzes and the labs, and then the synchronous lecture that will be recorded. You're welcome, Lakan. Did you have any questions about the material? Having done that lecture, did you think about or did anything that you saw throughout the week spur your interest or give you an aha moment? Or did you notice anything that you would have not regularly seen in your daily life that all of a sudden you put a motor control perspective on it? Okay. Well, the part is this is going to be your homework for this week. Like I was saying, not necessarily noticing anything, but maybe more aware of different movements. Okay, I'm happy with that. So if there isn't anything else in terms of the material or procedurally, we can get started with the lecture. I think the note taker is here, Karen. Okay, great. So let's get started with this lecture's material. So remember, we introduced the topic of motor control in learning last lecture. And we were discussing how a lot of the course is trying to understand how this new health field was developing ways to study motor control. And the idea would be to do studies that would be looking at the different variables that alter our ability to control movements and complete motor skills, and that would allow us to completely and more completely understand how our body takes in information from the environment and uses that to develop a coordinated voluntary movement. And so a problem with research was classifying different types of skills or motor skills and figuring out what class of motor skills are involved with certain types of movements, because certain movements are more difficult to learn than others. And so classifying skills was going to be the initial way to understand or group types of motor skills and give us awareness of, okay, well, these types of skills, gross skills, for example, are controlled in this manner, whereas fine skills are going to be controlled in this manner. Today, we're going to be moving forward with talking about, when doing research, how do we measure motor performance or our performance of motor skills? The outline of today's lecture is going to be talking about the principles of measuring motor performance. We're going to discuss performance outcome measures, performance production measures, as well as neural measures. And then the last thing we'll talk about is motor abilities, or the concept of an all-around athlete, and sort of what that research has led into. So the first part, like I said, is discussing the topic of how do we measure motor performance? How do we classify that someone is doing well at a motor skill that they've learned? Whereas how do we grade whether or not someone is progressing in their learning of that motor skill if they're going from amateur to pro, for example? It's difficult for many reasons, and we'll get into it right now. Because the question is, what types of characteristics could you use to measure the performance of a different type of motor skill? So let me ask you a question. Carolyn, with serving a tennis ball, how could you measure it and give it basically a score? Because remember, the principle of research is taking an experimental situation and then adding variables and seeing how different variables change or modify the topic that, or the item that we're studying. And by quantifying it, we're able to look at which variables modify or affect the thing we're studying in a better or worse manner. Okay, so Carolyn's saying, so if we wanted to measure or grade someone's tennis serve, we could look at it in parts to look at how the individual serve is moving and how precise it is. And of course, there's no right or wrong answer. They're all right, sir. They're all right answers. You're so right. So here we have, just in case you wanted to look at what a tennis serve is. So here we go. So that's a tennis serve. Look at it. Okay. Let's it from a different view. Let's watch it again. So Carolyn, we've been looking at the individual parts or movements of that motor skill. Remember, movements are the individual patterning of the joints, or the way that the joints are moving and the limbs are moving in completing that motor skill. So the motor skill is the thing as the whole, whereas the movements are the individual ways that the individual is moving their body to complete that motor skill. Because not everyone moves in the exact same fashion when completing whatever motor skill we're learning. So what other ways could we measure the performance of this person's tennis serve? Distance, yeah. What if they're doing it over a number of successive times? Accuracy, so whether or not it would be inside or outside of the court, and look at how accurate they are as a percentage over time. Speed, power. Carolina said the movement, so that would be maybe proper form. So maybe the form is getting better. They have better rhythm or coordination. They're all right. But this is the problem we're getting into when we want to analyze different motor skills, because we need to be able, yeah, exactly, Jessica, technique, consistencies of you're all right. But this is the problem, because we need to be able to grade the performance of the motor skill and look how that changes over time. What happens if now we change the color of the ball, or we dim the lights, or we make them unable to move their legs? Then we can look at how those different changing variables can affect their performance, and then we get a better idea of, okay, well, if they can't see clearly, or they can't see out of their one eye, then the performance is decreased so much. Clearly, that's involved in our control, where, remember, control process is taking the environment and then putting it into your brain with the pattern that we've remembered and then outputting it and being able to perform that motor skill in a wide range of different conditions. Yeah, and then that's exactly what we're saying, Jessica, adapting. So that's a little bit easier, right? Because it's a sporting technique. Sporting seems to be, because we're so used to grading sports, it's easier to sort of test. Now, what about a clinical example? How would you grade someone's performance when learning to walk after a stroke?
Patient has suffered a stroke affecting the right side of the body. Notice how the arm is held in flexion and the leg circumducts, moves in a bit of a circular fashion on the right side as he walks. Classic for upper motor neuron dysfunction. Patient has suffered a stroke affecting the right side of the body. Notice how the arm is held in flexion and the leg circumducts, moves in a bit of a circular fashion on the right side as he walks. Classic for upper motor neuron dysfunction.
So how could you grade this patient's walking ability and whether or not it's improving? Jessica's asking or saying grade based of improvements. So you could look and have them do tests after the fact. That's right. But what about evaluating the skill as it's in motion or real time? Like it is saying how the patient feels with their movement improvement. So there's sort of confidence, for sure. It's a subjective measure. And so there's problems with subjective measures because it's going to be influenced by how that patient is feeling that day or other factors potentially. Tyler's saying range of motion. Oh, we got lots here. Brian's saying gait. Sabanki is saying distance they're able to walk unassisted. And so all of these are right. Kayla is saying stride length, degree of flexion, and so looking at the actual movements themselves. And then Jacob and Alicia are both saying symmetry. Because in that video, did you notice that I think it was the left arm? Yeah, right arm.
Patient has suffered a stroke.
See the right side of the body?
Right side of the body. Notice
how
the arm is held in flexion and the leg circumducts, moves in a bit of a circular fashion on the right side as he walks. Classic for upper motor neuron dysfunction.
Avery's suggesting looking at the deficits clinically, so in terms of how they're walking, so gait analysis, it's perfect. Yep, and Brian, well, at 1% for sure. So all of these are right, but it's a little bit more, maybe I wouldn't say maybe difficult, but it's strange to try and grade performance in sort of a rehab setting. And just to point out how we use Gentile's taxonomy last day, at least they gave a standardized test. So this is all sort of in relation to the health field. Any questions so far? Veronica, any questions? No, that's a good. No. Never apologize. That's good. My goal is to have you all learn the material as well as can be. And I'm going to grade your performance by how happy you're feeling. So hopefully with what we've talked about just to introduce this lecture, you get an idea of why the measurements of motor performance are so important in terms of our ability to study them and understand the variables that are a factor in us being able to perform motor skills, because that's going to allow us, and this was what happened way before computers and different technologies, it allowed researchers to do studies to determine how we control our bodies. So performance assessments are important for research in that way, the quantitative analysis. They're also important, just like you all said, in assessing performance clinically or in a coaching situation to assess sort of the capabilities and limitations or the level of whatever participant or patient we are researching or looking at that time. It also allows us for determinant of progress. So if we can evaluate performance, it allows us to judge whether or not the person is learning at an appropriate rate. because learning is inferred through observation. It's not something that we can like objectify immediately. So there's a variety of different ways that we can evaluate motor skill performance, just like all of the examples that we've come up with right now. We've come up with a list of 30 just off the top of our heads. What we're going to do is look at sort of the main ways that researchers initially tried and started to evaluate motor performance and how it's evolved through the years. Now, remember, we were talking about individual movements, we talked about the skill, we talked about how well they did overall. We can categorize the level of analysis of our motor skills based on what level we're evaluating. And remember, we learned these terms last week. We learned motor skill means action means skill. So we can learn to evaluate the skill as a whole. We can look and analyze the movements themselves. So the movements are the individual movements of the limbs as the individual is performing the motor skill. And we can even evaluate the neuromotor processes. So there's different levels of ways that we can analyze or measure performance, but there's two general categories of measurements for motor skill performance, and that is performance outcome measures, and the second is performance production measures. The first one, performance outcome measures, are looking at the overall performance of a motor skill. So they're called outcome measures because they're concerned with the overall outcome of the motor skill. So think of, and this is the picture in the slide, like sort of the judges judging, I think, a gymnast or a figure skating routine. They're giving a score on the overall motor skill. So outcome measures are concerned with accomplishment of the task. And that is what we're all probably generally more familiar with, are outcome measures. One thing that outcome measures don't tell us is indicating the movements that were used to accomplish the goal. So if this athlete got a 75 or 76 out of 100 on their gymnast routine, it's not telling you what moves they did in the routine. Or if this was figure skating, it's not telling you how many flips or turns or triple sow cow or any of those moves. It doesn't tell you what happened in the actual routine itself, but it's giving you an overall score or outcome. It also doesn't tell us anything about the neuromotor processes. Does that make sense, everyone? Awesome. So in that sort of theme, performance production measures are those measurements that are related or interested in the movements that were used in the achievement of the task. So performance production measures are going to look at the individual movements of the bodies, or it's going to identify the different neuromotor processes that were sort of occurring in the accomplishment of the task of the motor skill. And then this is just an example of the general and more frequent outcome and production measures that have been used in research. And these are the ones we're going to talk about today. So let's first go into the most common performance outcome measures. The first one actually was reaction time. And I know that doesn't seem like an outcome measure or like a score to give an overall performance of someone serving a volleyball or someone brushing their teeth. But reaction time was really important because it is a measurement that allows us to look at how much time was required for that person to process or initiate movement. Now, have you all sort of heard the term or the concept of reaction time before? Yeah, so we're going to do an example, but it takes a little bit of time. If I want to go and do something, a motor skill, there's an amount of time that my body is processing before I can initiate movement. So if you can calculate what that time is, you can change variables that are around, or the regulatory conditions around someone performing a motor skill, and you can look at whether or not the reaction time increased or decreased. So reflex time is a little bit different. Reflex implies like a reflex where you're not controlling. So remember, motor skills aren't reflexes, they're controlled movement. Similar, yeah. A lot of these words we use interchangeably, but when we're looking in like a more, specific clinical or educational way, the words are specific. So if we were to look at, I don't know if you guys remember from the video last week when they were looking at choice versus reaction time. When you have more choices, when you have, a stop sign versus a traffic sign that has 3 different options, your reaction time increases. It takes longer for you to process it. So you have a perfect measure to look at what variables affect your ability to perform a motor skill. So that's why it was used initially as the first one, and it has been used consistently because it's such a good measurement to look at or understand what are the variables that affect our ability to process and ultimately complete our motor skill. So reaction time, it has been sort of argued what was the minimum required reaction time. And I bring this up because it's led to significant rule changes in sprinting over and over and over throughout the years because they keep realizing that there is a minimum amount of reaction time. And that minimum amount of reaction time is less than 0.1 seconds, so 100 milliseconds. So I don't know if there's any sprinters or anyone that watches Summer Olympics or sprinting or running or track and field, but all of these blocks have a timer that or a sensor that will count the time after the gunshot to start the race, the amount of time that it took for the sprinter to leave the starting blocks. And if that time is less than 0.1 seconds, it counts as a false start because it means that the person wasn't reacting to the gunshot, they were anticipating. And so that's why we always have all those false starts, and they redo the race over and over again. I think now you can't have any faults, right? Does anyone know that? I think now one fault and you're kicked out. No sprinters. Oh, it is true. There you go, Jacob. Okay, Jessica thinks it depends on the race. It probably does. I don't know. You can find out. And so this is why reaction time was utilized so heavily and has such a history in motor control research. Because by calculating the reaction time and seeing if it increases, we can understand that obviously if the reaction time increases, there was more processing required before the person could initiate the motor skill. So it can infer the amount of preparation required, and then it can also infer, because what they did in research was they started changing things in the environment, and if it changed the reaction time, that led to more processing. So obviously that's something like a regulatory condition that's important in our ability to complete that motor skill. I don't know, is Jacob a runner? Or does he just run his mouth? Just kidding. Jacob's a good guy. Okay, so here's a common examples of different types of reaction time situations. And I don't know if you guys remember this from the video, but there's 3 options in terms of types of reaction time. There's simple reaction time, whereas the presence of one stimulus or signal requires one response. And this is the fastest of the reaction time, like a start signal. Choice reaction time is a situation where we have more than one signal or stimulus, and each signal or stimulus requires a different action. So that would be something like a traffic light where we have 3 different lights, and then each of the 3 choices means something different. Green means go, yellow means go faster, and red would mean stop. Discrimination reaction time is a type of choice reaction time where you have multiple signals, but only some of the signals require a response. So your body still has to process, okay, signal coming in, does this signal cause a response or do I block it out? So visually, here we have our examples of the different types of reaction times. And let me ask you, Leka or Sandra, of the 3 types, which would lead to the the fastest reaction time? So the least amount of processing. Simple. Yep. One signal, one response. Whereas if you have 3 different signals, your body has to look at, okay, what color is this? What does that mean again? Oh yeah, it means this. So it's more processing. One thing that they learned in research, and does anyone know what EMG is, or electromyography? Okay, perfect. So EMG is just reading the electrical potentials in the muscles. By using EMG with reaction time, it allows us to sort of divide up the reaction time into the different parts. So there's going to be an amount of time where is processing in the brain, and then there's going to be another amount of time where the brain's processed it and is trying to send the signal out to the muscles, and then the muscles get the signal and are trying to contract. So by using EMG, we can do what's called fractionating the reaction time to get an even more accurate estimation of action preparation, or the preparation or processing in the brain, by dividing up the reaction time in premotor time, or into premotor time and motor time. So if we were to use, let's say we're doing like a hand reaching task, and then I would put EMG on the biceps and then do choice versus simple reaction time and look at which factors changed reaction time. By having the EMG pad on the muscle, what I could do is it would start reading electrical potentials in the muscle before there was an initiation of movement. Because remember how muscles contract, they contract, and it takes a little bit of amount of time for the muscle to contract fully, up until a point where it can put the torque or the tension onto the bones, and then we get observable movement. So by using fractionated reaction time, or by using EMG, we're still measuring reaction time, but we can sort of break it down into the premotor component. So this would be all processing, and then this would be the amount of time that's required in getting the muscles moving. So all of the processing in the brain, that signal getting it sent out to the muscles, would be in the premotor component. Does that make sense, everyone? It just allows for a much more accurate signal when evaluating reaction time. Because what researchers did was they took this reaction time, this premotor component, as the information to infer how much processing the brain has to complete. Everyone good? I think Jessica said yes. My email's blowing up. I'm not sure why. There's other things. I don't know if any of you got the textbook or the free PDF, but different studies can introduce different measures in relation to reaction time. So we will see some studies that evaluate movement time, which is the interval of time that it took to move, to look at like accuracy versus speed. Response time is reaction time plus movement time. And so in some studies, this was important to look at the speed accuracy trade-off. Oh, Lekka got the textbook. That's awesome. So you can always share different examples if you'd like for the class, for those of the students that don't have the textbook. But by using movement time and response times as different examples of types of reaction time, we can look at and evaluate the speed accuracy trade-off. You got us, team member. And so this diagram here is just evaluating or sort of describing or demonstrating the different measures that we've talked about with reaction time here. So we have our premotor time. We would have our motor time, initiation and response, movement time, and total response time. They're just different variables that were used in research. I don't know if this is going to work, but did someone want to test their reaction time? If I share my screen, will it work? Or can you share your screen? Can you share your screen and try it? Okay, so Lekka, I will stop presenting. Click on the Just Park one, and then share your screen, and let's see how good your reaction time is. Deal? Okay. Make sure that you close all your tab on your browser to make sure, okay? So share screen and then hit just park, or human benchmark is just one that just checks the reaction time. Carolyn, you have the reaction time of a 61-year-old. Is that what it said? Are you sharing your screen? Oh, there you go. I can't see. Oh, there you go. Oh, hold on. Okay, let's do this. You got this, Leica. Let's go. You got this. Positive. Okay, so okay. We should do a test to see if positive reinforcement, silence, or chirping will improve or decrease reaction time. Now let's try positive. We got to manifest it here. You got this. You got this, buddy. Yes. You're amazing. Oh, I don't know what happened. What do you gotta do? Oh, it's okay. Oh, wow, that's still kind of bad. So it's 600 milliseconds almost. It's okay. So you guys want to try me? I don't know. Let's see. Let's see how the prof does. You had it, buddy. Okay, wait. How do I do this? Copy. You got 38, Daniela? Wow. Okay, let's try me. Present a window. Mozilla. Okay. I don't know if this is working. Great, hold on. So if I do this, you guys see that? If I go back, is that not coming out? Okay. Okay, ready? Let's do this. Okay. So Daniela got 28. Here we go. I'm so good at this. Here we go. Dear. Okay. Yeah. Okay. I'll take it. Now, I don't know if I'm that good. It's because I watched you all do it. So therefore, I learned through mimicking. There you go, Jessica. I'm proud of you. We're all proud of you. I'm now going to share the lecture again. You got 22? Okay. Is that right? Did it? That's funny. You're who can program a bot to do this? That's awesome, Nolan. Okay, can you guys see the lecture slides again? Okay, good. Perfect. So that's an example of why reaction time is used. And so we can look at different factors and analyze our reaction time. And therefore, certain things take certain amounts of processing. And so it's a great measure to start using in early research. There's other things like error measures. And so measures can allow us to look at spatial and temporal errors. The good thing with error measures is they allow for evaluating like bias and consistency. So remember we had talked about how as someone is learning a motor skill and they improve, they're more consistent. At least error measures, which is a different type of outcome measures, will allow sort of evaluation of how consistent someone is becoming. So therefore inferring learning. When using like sort of these one-dimensional error measures, it's difficult, but keep in mind that early research, they were looking at like like markers on like a time with walking or markers on a ruler. They were looking at very simple motor skills. Absolute error is looking at the difference between the performance minus the criterion. So you would calculate a quantity of error in each trial. And what you do is you take the absolute value of those and then divide it out by the number of trials that you did. And it would give you a sort of absolute error measure, or the average error. And it gives you a measurement of accuracy. Constant error is when you take out the absolute measures. So if, let's say, the criterion you have to get to is like 0, and so your trials are like, results are -1, 2, -3, 2, -5, 5, and sort of going back and forth below and above whatever your criterion is or your measurement. By taking out the absolute values, it's called constant error, but you would get either a positive or negative value. So it gives you an idea of performance bias, whether or not you're always overshooting or undershooting a target, for example. I know this is difficult to sort of visualize because it's only one dimension. Variable error, and I don't know if you guys did this in stats, quantitative reasoning. We do take the standard deviation. So you look at the average of the deviation from the mean, and then that would also give us our measurement of consistency or variability. It's difficult to sort of grasp when you're thinking about this in one dimension, but it's easier to look at when we're looking at sort of two-dimensional goals. So think of a motor skill being like darts, okay? What you could do to look at the error is you would just say if the target is the bullseye, you would take each trial or how wherever dart during each trial lands, and then you would look at how far it is away from the target. And then you could take that as a measurement, and it gives us our radial error. Because what you can do is take all the different trials and calculate the distance it is away from the target, and then average that out. So on that note then, so let's say this is darts or golf, I guess it doesn't really matter. So Josephine, which golfer would you say is better? Let's say this is the target, and then these are the trials, B. Okay. Shane, Emily, everyone's saying Jacob, like everyone's saying B. No, I agree with you. If you were to take the average of how close it is to the center, the average of golfer A works out that it's right in the middle. So just taking the averages sometimes doesn't really tell us the whole picture, because golfer B is actually way more consistent. And so I agree with all of you that golfer B is actually the golfer that learned more or learned better or has better performance. So this is an example of someone that is consistent and biased. This one person, because they're biased because all of their shots went to the right, whereas I would say that golfer A, even though their average is right down the middle, I would say that they're inconsistent because each shot is sort of in a different spot. Does that make sense? Hopefully not too difficult. Perfect. Go squad. So now this is a little bit more difficult. What about error measures for continuous skills? Skills that take, remember, there's no like beginning and end. How do you come up with a number for those? The one that they did in research and they've used the most is root mean square error. So remember, continuous skills are something like driving on a car or running on a track. There's no set beginning and end. It's like repetitions of the same movement. The most common one that they do in research is a pursuit task. So I don't know if any of you have done this in any of the studies at Ontario Tech, but where you have to follow along a target with a cursor. And so what they do to analyze performance is look at the error being the distance between your cursor, or your pointer, sorry, and the target. So if you cumulatively look at the error over time, it'll give you Like, so see, this is where their cursor was, and then this was the target, the solid line. And so the worse they are, there's more of a distance, or there's more error. So you can cumulatively look at the amount of error divided by time, and it gives us sort of an average amount of error for a continuous scale. And then LECA, you'll see that in the textbook as well. They talk about some studies like that. Yeah. The point of today's lecture is just to give you some ideas and some examples of the different measures that they've utilized. Because then we'll talk more about them as we continue on in the lectures, obviously, but what those measurements and studies using those measurements, how they've told us about how the body controls movement and what they've sort of inferred, or what they infer for us. Now let's talk about some performance production measures. And so remember, production measures are concerned with the movements or the neuromotor processes of the scale. And so you've probably seen a lot of these terms before, but examples of measurements that will look at the movements and neural processes include kinematics, kinetics, this is from biomechanics, and then neural measures, maybe from biomechanics or A&P. So does everyone remember the term kinematics? Kinematics are ways to describe the movement without looking at forces. So this is the movements of the limbs, so displacement, velocity, acceleration. It tells us the movements of the body. Kinetics is analyzing forces, so the forces on the ground and the forces in the body. Looking at the kinetics, you can get an idea that someone's becoming more efficient in their movement. And then neural measures is looking at EMG and then also brain activity measures. So like EEG and functional MRIs gives us an idea of what's going on neuromuscularly. So these are the different sort of examples that we're going to talk about for production measures. So have you taken biomechanics yet, everyone? Okay, perfect. So then you know, right? So we're not going to get too heavy into it. There's no numbers in this course. It's just talking about kinematics. And kinematics is perfect because it's the analysis of the movement of the body. And so if we do kinematics, we're actually looking at movements of the body. It's perfect for this course. And there's different ways to do kinematics. And then it originally started off as photography. So when they, this is like in the 1800s, when they figured out a way to do successive photographs, like now you can't just take a video on a phone, right? They had the like light and the gunpowder, and they had to take a photo that way. I'm just thinking of old cowboy movies. I can't even think of a cowboy movie. I'm thinking more of cartoons. But anyway, this is how they would do it. So they would take successive photographs. Yeah. Jessica has PTSD from biomechanics. That's fair. But by doing photography or looking at quick photos, you get a better idea of how the body's moving. Because up until that point, it was just through observation. By doing photography, it gives us a better idea of how the joints of the body and the limbs are actually moving. And Edward Muybridge was the, so this was a big scientific question. And so they were, there was a question as to whether or not there was a period in time if when horses ran, if they would, if there was a moment in time where they wouldn't be in contact with the ground. Oops. And so this gentleman in, I don't know, some point in the 1800s, what he did was he did this photography method, and he was able to look at the gait cycle of the horse, and he could prove that that the horses, there was a period of time in the gait cycle that the horses were sort of all in the air. Can you guys see that? So then as they were trotting, they would always be in contact with the ground. And as they got faster and faster, there'd be a point where there'd be like airborne almost, right? Makes sense. The same thing when we're running. But up to that point, it was hard to prove that, right? Because you're just watching a horse move as fast as they can. It's like they're arguing with each other. And like, I challenge you to a duel, I'm right. Fun fact, this gentleman, he shot his wife's lover and was in jail. And so that ended. Yeah. He was too busy taking photography of horses, poor guy. Yeah. It's not really fun, I guess. A little bit morbid. Danielle, do you have a fun fact, or do you have more to add to it, or you're just making fun of me? Both are fine. That's fine. Fun fact, Daniela is chirping the prop. Goniometers are a term that are described as like measuring joint angles. So I don't know if you guys are familiar with this. A manual goniometer to measure joint angle and check someone's range of motion. You can do this clinically in an experimental setting or a research setting where it can measure the joint angle changes. So it's measuring the angle between here and here over time. He's still talking about, okay. Oh, right hand rule, sine cos. That's probably stressing you out. Is it sine or cos? Accelerometers are, so this is a little piece of machinery here. It'll measure the acceleration and you would put it on the body. And so it would give you an idea of how fast the joints are accelerating. This is a positive moment. I don't know why they just didn't say counterclockwise or clockwise, but right hand rule. Because the right hand, if you close your hand, it goes around your thumb. I know. Huh? I taught about biomechanics for a little bit, so I feel your pain. These are mechanical systems. So this is another way to measure sort of the angles of the joints over time. And remember, in research, what you would do is you would have a goniometer, or you would have an accelerometer, or you would have some of these mechanical systems attached to the participant, and it would record the movements of whatever of the body, whatever part of the body this machinery was on. So it would allow us to take kinematic measures or production measures of the participant as they're performing research. Here we have an example of a study. So I actually did, I worked in a lab with Michael Holmes. He used to be a prof here. But this is him. And in his research, what they were looking at was using this machine here to measure the angle of the spine when they're bending and lifting. And then what they would do, so he was out east when he did this research, and they would look at lifting this on a moving boat. So they had a boat simulator that would like rock around like a theme park ride, and they would look at how the angles of the spine would be different when the boat was stationary versus in motion. And it would look at how the handling of materials in a rocking situation leads to more forces and therefore more injuries. They could prove it. And then they would come up with ways that they could show, oh, if you did this or they use these types of boots, there was less motion, therefore it's safer. This is a magnetic system, so this looks at like angles. So versus an accelerometer, this would be a test. So this is right here. This is actually part of the research I did when I was, oh my gosh, 12 years ago. But what it would do is look at, so this person's gripping, it would look at how their hand is changing in terms of their angles. The most common thing that we do now with kinematics are motion cameras. So we're all familiar with this, right? Where you would analyze someone's motion and then they would put that into animation or like video games. This is kinematic measures. You're looking at someone's movements. What they're doing is they're recording how the body's moving and then using that in an animation. But you could also use this in research. Passive means that, see how there's markers? So they just shoot an infrared light and then the camera is able to pick up where the different markers are. And so they have a computer program after that would, in each frame, point out where all of the markers are. So it's a passive system because none of these markers are electric. They're not shining. They're reflecting the light that's being shone onto them. Shone, is that a word? OptiTrack is an active one. So this is what we use in the labs. And so with the markers, for this, like for example here, only one marker is on at a time. And so the problem with digitizing like back here is that like look at Sidney Crosby going all around. There's gonna be frames where you can't see all of the markers. And so the computer would have a hard time trying to figure out how the body moved. You have to go one by one and sort of reevaluate what the computer did. With active systems, you don't need to do that because so with this one, there's multiple different cameras that are picking out the markers. This one, only one marker is on at once because they're actually electric. And so you would know what marker is going on. The problem with these ones is that you can't move as fast because it takes, you have to move slower so it picks up everything. But these are all the different things that exist. And so again, remember the point is that these measure kinematics. And that's going to help us in motor control research because it's going to give us an idea of how the limbs were moving. And then it can give us coordination sort of information. It can look at how someone's changing over time of learning a different motor skill. Here we have, you can take that information and do angle diagrams. This way is you. So if you look at here, we're looking at an angle diagram. So the angle of the knee versus the angle of the hip. And so in some research, what they do is they looked at being able to use this measurement over time as a measurement of coordination. So you could give someone a measurement, oh, this is how coordinated they are, have them practice and then measure their coordination again through kinematic measures. Kinetics, also biomechanics, is looking at the forces. And so with forces, like if you think about analyzing someone's jumping or someone's ability to play sports, if you look at the forces, it can give you an idea of improvement because the forces are more efficient or the forces are greater when they're kicking a soccer ball or hitting a baseball, for example. And so the machinery that we use to analyze kinetics or forces in the lab are things like force plates, force transducers, and strain spaces. I think you guys have done, in biomechanics, did you guys do the gait cycle? It measures the force of when you're stepping. So that's a kinetic measure. I think you guys are all asleep from the biomechanics talk. Did you? Well, that's good. That's cool. Oh, okay, just the gait cycle. That's fair. So just analyzing the gait cycle like that would be a kinematic measure. Measuring the forces of the pressure is a kinetic measure. The last thing that you can do to analyze the production measures or a production measure when analyzing movements is the neural measures. And this is going to give us an idea of the neuromotor processes involved in performing of a motor skill. And so they're broken up into two different categories: muscle activity measures and brain activity measures. The brain activity is going to look at what parts of the brain are active during a motor skill performance, whereas the muscle activity measures are going to be looking at the electrical potentials in the muscles when we contract them. Both are neural measures because they're looking at the neuromuscular system. I don't know if you guys all remember this from neuroscience, but we all have motor units. So functionally, our lower motor neuron and the muscle fibers it's attached to are one unit. So when we activate a lower motor neuron, that action potential continues on and contracts all of the muscle fibers. So when we're looking at EMG, we're looking cumulatively at all of the activity of the motor units. So common muscle activity measures are EMG. Whole muscle mechanography is a way it is measuring vibrations. And so what it can do is it can look at the displacement of the muscle belly over time. The reason why this is why sometimes this is used is because it's not super accurate, but it gives an idea of muscle fiber composition. So it could look at a training regime and looking at someone like, so they want to do like plyometrics and learn and jump and have a better vertical when like dunking the ball or something. this would give a better idea if the composition of the muscle is changing over time. We're going from like slow twitch to fast twitch, for example. Near infrared spectroscopy is has anyone ever been in the hospital? Hopefully not. But you know the sensor, the red light sensor that measures your blood oxygenation level? That's that. Yeah. And so what you can do is you can use it. Yeah, Jessica loves it. It's a cool bit of, because it looks at the light and how it's refracting, and then it tells you whether or not there's hemoglobin or not, when it's oxygenated, sorry. And so it can let you know about what part of the muscle or brain is being used. Here we have an example of a tracing of EMG. So here's us. So this would be a force measure. This would be, let's say it's a gripping technique or something, right? Yeah, actually, that's a good point, Xavier. This technology is now, let's see what it says. This one is a 5, I think, or 4. The newer ones can do more stuff. This one is 2 years old. Yeah, I think that might be it. Does this one measure? No, this one, yeah, this one measures heart rate. The new ones, Jacob, will measure oxygen, which is that. Saphir, huge flex. He's got an Apple Watch 7. Here's an example of using EMG in a study. So remember we were talking about the changes in muscle activation, or looking at how we can use production measures to get a better idea of how people are changing when performing motor skills. Here we have an example of EMG being used in a motor task, where what they're doing is they are evaluating different muscles and then having them do one motion and looking at which muscles fire first. So the task was to just raise their arm, and they looked at which muscles fire in which order. And when the task is just raise your arm, what they found is that the first muscle to activate was the ipsilateral biceps, then the anterior deltoid, then the contralateral biceps femoris, so hamstring. And why would that be? Stability, right? So if I want to raise my hand, I first got to contract my body to prepare to be stable for that motion. Yeah, exactly. Jessica knows. But that's a neuromotor measurement, and so you could analyze stuff like that, and it gives you a better idea of whether or not someone's performing better. Or think of this: that clinically, if we're trying to teach clinical or neuro patients to get back to daily living, this is going to give us a measure of, oh, well, this is what the difference is. This is where their deficiency is, and it gives us an idea of their limitations, and it gives us sort of a guide on what to treat. This was my study. This is wait, when was this? 2010. It's back when I was 17. Just kidding. This study was looking at the activation of the rotator cuff and the different shoulder and arm muscles in different gripping tasks. And so what I had people do was hold a weight, grip, and hold a weight without gripping, and different angles of abduction flexion. And it would look at how the rotator cuff activation changes. We were funded by the automotive industry, like as a group in Canada, and they wanted to look at why people with shoulder injuries were getting so injured and others were not. And so it was that when the gripping forces, makes sense, right? So if you hold your arm out, there's a high number or high activation already, but if you grip, the amount of activation of the rotator cuff required is so much more. So a factor in the development of people in the automotive industry that were getting really hurt was because they were having to hold their arms at weird angles, but also grip hard in that time. I was kidding, I wasn't 17. brain activity measures, and now we're not talking about the muscles, but we're looking at the activation in the brain, because these are great measures, because it allows us to figure out what parts of the brain are active and how that changes. So what, like, remember we were talking about how reaction time gives us an idea of processing? Using brain activity measures may actually allow us to look at, in terms of the motor control process, what parts of the brain are active. Have you guys ever heard of, has anyone ever heard of EEG? So it would be Bernadette's studies. Perfect, yeah, where you have all the different sensors on your scalp, and it measures the activity in the brain and sort of where it's coming from. So it's really useful. The problem with EEG is that it can only touch the cortex, and so much of our control, remember we have a regulatory centers like our basal ganglia, pardon me, our cerebellum is where we're learning stuff. It can't really hit that. It is uncomfortable to wear. It's not COVID. I just need more coffee. It's easier for me to wear because I don't know if you noticed this, but I don't have any hair. Transcranial magnetic stimulation is another way. I don't know if you guys, yeah, no, it's true. Well, it's not by choice. Well, it is, but medium. Yeah. Yeah, I did it for the research. I'm just like so committed to learning. Did you? Wow. Carolyn did a study with EEG and she lost some hair. Oh, yeah, of course. Well, that's what they were looking for too, because they found they did an analysis. Sabanki is saying that I don't have hair for the modeling contract for the textbook, and that's true. Has anyone in the class used transcranial magnetic stimulation? Hey, what's going on? Transcranial magnetic stimulation is using, it's basically like a little bit of a wand, and it can discharge magnetic energy. And so what that would do is disrupt parts of the brain, and then you can have someone do a motor skill, hit a part of the brain and see what changes, and then that would infer whether or not that part of the body would utilize that. That motor skill would utilize that part of the brain in motor performance. Here we have transcranial magnetic stimulation going on. These are the final ones, and this is important because it allows us to look at sort of the brain in 3D. So EEG was just the cortex, when so much is happening just at the cortex, but also in the insular lobe, what's going on in the brainstem and cerebellum. These will look at the inside of the brain. PET is sort of imaging technique that looks at blood flow in the brain. MRI is, so functional MRI is looking at, does anyone have an MRI? So MRI is looking at the water content, and you're able to see everything in sort of like great clarity. You can use that with some, when you drink a certain dye, and you can use that to look at blood oxygenation levels in the brain in a 3D sort of map. And then so what you would do is you would do the MRI while you are performing a motor skill, and then use fMRI to look at where the blood is, or the oxygenated blood. That would tell you that that part of the brain is being utilized potentially. The most accurate and most recent way to analyze the brain is magnetic encephalography, so MEG. It looks like this here. And so what this does is it gives you a measurement of the electrical activity in all of the brain. So it's exactly what we want. So this is the future of research. The problem is if we look at this machine, there's not a lot of different types of motor skills that you can do while being hooked up to this big machine. I think I have a video here showing this. This is the future.
Brain activity is basically just electricity. So measures the magnetic fields that are generated by brain activity inside your head. It's one of the few ways we have to get access into the internal workings of your mind. Lock the sensors, yeah. Okay, we're going to play you a sentence and we're going to ask you to covertly repeat it. That is, imagine saying it covertly.
The MEG has a built-in helmet of 160 magnetic field detectors that scan and record the subject's brainwaves every time she imagines a given word.
The book is next to the glass.
The MEGs are looking for a signal given off by neurons that's incredibly tiny, a field that's 1,000 times smaller than a refrigerator magnet.
Every millisecond, that is every thousandth of a second, we're recording from the entire head, from all 160 channels. It's an enormous amount of information that we then have to sift through to make sense of.
Their goal is to isolate clear efference copies for every word imagined by the subject.
You don't just know some word and its sequence of sounds. All the information associated with that concept suddenly comes up. Imagine yourself saying the word cat. You had a cat called Fluffy when you were a kid that threw up a lot on your bed, or you hate cats, you love cats. So it's not a needle in a haystack. It's like a needle in 10,000 haystacks.
With each word that Popel deciphers,
Okay, keep going.
we grow closer to a future where advanced mind scanners could lay bare our innermost thoughts.
It will redefine doctor-patient relationships. It will help redefine lawyer-client relationships. It will certainly have an impact in criminal justice investigations.
Imagine you're going to the airport. TSA could figure out whether you were a terrorist or not. And it shouldn't be the case that TSA, by default, gets access to our thoughts. It would only be that people who want to participate in this sort of accelerated screening can opt into it.
This is an example, I mean, it was kind of dramatic, but talking about MEG or magnetic encephalography. And remember, it's important because it's showing us specifically the neuron firing in the brain. So it's telling us exactly how the brain is working. And we can use that in motor skill analysis because we can look at how our bodies or how our brain is processing the environment when performing different motor skills. Any questions so far? Is everyone okay? Awesome. The last thing we're going to finish up with is motor abilities, or the concept of the all-around athlete. So hopefully it interests you a little bit. We're talking about motor abilities. Understand that the term or the adjective ability, or the verb, sorry, is a general trait or capacity of a person. So we could say that someone has the ability to do this. What does that technically mean? It means they have an enduring characteristic that would generally predispose them to complete a whatever task. So they have a good artistic ability, means that they would probably be able to draw something if you ask them, for example. When talking about someone's motor abilities, we're talking about enduring characteristics in relation to them performing different motor skill. And so what research wanted to look at was that, is there a predisposed motor ability in people? Or, you know how like some pro athletes are just seem to be good at everything, right? Everyone has a friend, or that you might be Jacob and be that person that just seems to be really good at any sporting technique they're asked to do or shown to do. So does that mean that all individuals have a generalized motor ability? And if they do, then they're just generally good at all motor skills? Or because if that's the case, then we could come up with a test to see what someone's general motor ability is and then train them. Or do we have individual motor abilities that are, you know, a variety of different things like timing versus speed versus hand-eye coordination. Are there multiple multiple different motor abilities that come together? And so what research wanted to look at sort of this concept. What do you guys think is more accurate? Because there was two hypotheses. That there was the general motor ability hypothesis initially, that there was just a measurement of someone's motor ability. It was either high or low, and it accounted for all the different types of motor skills. Or do we agree with the specificity of motor ability hypothesis, meaning that we have there is individual different motor abilities, and every individual has a varying degree for each type? Leka is saying he thinks that, they think that everyone has an innate motor ability. So Leka is saying that she thinks that everyone has an innate motor ability for survival, but some people are built with better motor skills that could relate to their genes. I think that's true. I think that genetically, there's for sure a predisposition in our genetics that will allow us to complete better or compete better or worse in different skills. Because how many stories have we heard of, their father was an athlete, or they come from a long line of athletes? Obviously, something is being sort of passed down. But if research solved this sort of idea, then we could figure out the best way to sort of train people. So remember, just to clarify, the general motor ability hypothesis suggested that there is one generalized motor ability that each individual will have, and that will predispose them to their performance in learning and achieving motor skills. The specificity of motor abilities hypothesis suggested that there was all different types of motor abilities that you could have, and they were all independent of each other. So just because someone was good at hand-eye coordination doesn't mean that they were good at generating speed, for example. And so what research did was they looked at testing individual motor abilities and then seeing if they're related to each other. So static posture versus dynamic posture, or internal timing versus external timing. And you're not going to be tested on these specific studies, but what the different research studies looked at were comparing participants' motor abilities against each other. And what it showed is that just because someone is good at static posture doesn't mean they're good at dynamic posture, or static balance versus dynamic balance, or internal timing had no correlation with external timing, and so what that meant was that we have a sort of proof of the specificity hypothesis, meaning that everyone has a varying degree of motor ability in all of the different motor ability options that are available. And so therefore, what are the different motor abilities that we all have? How many different varying degrees of motor abilities are there? And then the other question is, what about the all-around athlete then? So if there isn't just a way to say that someone has a generalized motor ability, how do we, this is Bo Jackson, but how do we defend or discuss or talk about how all-around athletes exist then? And then I don't know if you guys have any answers on that. If there isn't a such thing as just someone's like motor ability in general, how do we defend the presence of all-around athletes? Yeah, the passion or motivation allows us to become experts. Jacobs are on the right term. So he's saying that practicing different disciplines or skills translate to different sports. And what they found was that generally, if we think about sports, they all kind of have similar abilities required, right? All running, jumping, hand-eye coordination, motivation. So the way that we can sort of explain the presence of all-around athletes is that even though there's no such thing to describe someone as a set motor ability, all of the sports that are things that we're used to, they all follow along the same motor ability. So those all-around athletes have a high ability in those specific characteristics that seem to be similar in different sports. Yes, it is Jacob's exactly right. The one-to-many concept. So those abilities that all-around athletes have can be used in a wide variety of sports because a lot of them do the same sort of thing, physical activities, same physical characteristics. Like I was saying, the gross skills are similar, but the fine skills are specific to sports. That can be true too. So the gross, so on that term, these gross skills, so the gross movements are similar in all the different sports. So if an athlete is good in those skills, he's going to be able, or she is going to be able to perform well in each of those different sports because they're all very similar. And research went on, so here's the word taxonomy again. So research wanted to look at ways to analyze what are the different motor abilities that you can have then? Is there like a finite number? And so here's an example. They wanted to develop a taxonomy of, okay, well, these are the potential motor ability options, and then we can grade people on each of these categories, and then we would get a sort of a motor ability number for that person. What this research led into was standardized testing. So think about, does anyone know any firefighters or any career that requires standardized testing? Oh, awesome, Georgia. So they all have to do standardized testing, right? Paramedics, cops, probably lots. Athletes, sure. But with standardized tests, instead of saying someone has one number that's an ability, what the standardized testing is, for example, they're looking at the requirements of that particular sport or of that particular career, and they're looking at what abilities are required. Of all the different abilities that you could have, what abilities are required, and then testing the person on those. If the generalized motor ability hypothesis was true, then if someone was good at bench press, then they'd be good at carrying the ladder or holding the hose for a fireman, for example. But that's not the case. Standardized testing looks at the career and what specific abilities are required, and then tests those ones. Does that make sense? I think that was a good analogy. Awesome. Because this concept of standardized testing also sort of related into sports, where with sports, what you could do to speed up learning is you'll take whatever sporting technique, so tennis serve from the beginning of class, that example, look at what abilities are required, and then you could just like individually practice a bit of those individually and put them all together. Jacob, RBC, Royal Bank of Canada. What's RBC? Oh, okay. That makes sense. Whoops. But yes, that's exactly what that is. Yeah. Yeah. So now we see this research was done way back, right? So those athlete development. So everyone's talking in the group chat now about RBC as an athlete training program, but now we see how the basis of all those training programs started. It was through this sort of research. Interesting, right? I mean, obviously, through observation, people had an idea of all of this stuff, but this was just proving it. Awesome. Any questions, anyone? That was the end of the lecture. Kylie is asking, will there be any practice midterms available? I think there is one. Yeah, and then also the quizzes, where you can go log in, log out. March 9th. Awesome. Okay. There should be a posting, Jacob, about who your TA is for the drop-in session. But remember, labs are done on your own time. Yeah, so it's just look at the due date. So you just do it before then. Yeah. Awesome. Good. I hope everyone enjoyed the lecture, and I'll see you next week. Oh, Jessica's asked a question. The last slide talks about how the usual skills like grip, stance will help a person become overall better at the before. Yeah, like, so think of it like if you could look at the skill of whatever they're trying to do, and then rather than just keep having to practice, you could break it down and look at what is required and individually try to have them practice the individual things that were required for good performance, and then put it all together. That is the basis for standardized testing. So like for standardized testing, the basis is looking at what's required for the job and then coming up with tests rather than practice, coming up with tests to show that those individuals can do those things. Yeah, awesome. Okay. Bye, everyone.